All right, section 2.4, symmetry. Okay, so we're talking about symmetry as it relates to graphs. Okay, so the first thing I think we should talk about before we even get to graphs of functions, right, lines and other shapes, first let's talk about kind of what we mean by symmetry when we're talking about points. After all, graphs are just a bunch of points connected, right? So let's see, let me draw a plane here, x and y. Now I'm going to put this one point, let's see, at 3, 2. Okay, that's going to be my starting point here. Okay, if I wanted to say that I had a point that was symmetric with respect to the x-axis, okay, that would mean that I have a point that is located with the same, I guess, dimensions, right? It's to the right 3 and up 2, except instead of going up 2, I want to go the opposite direction. I want to go down 2. So I'm going to clear all that out the way, and then say my point would be located 1, 2 down. There we go. Okay, so it's symmetric with respect to the x-axis because if I look across the x-axis, I find the same point, right? It's been reflected. That's another way to think about it. It's reflected. It's as if you look in a mirror, right? As you get closer to a mirror, the closer your reflection gets to you, right? So that's the idea. Okay, so that's symmetric with respect to the x-axis. What about symmetric with respect to the y-axis? Okay, well, same idea. Okay, so I want to take this point and reflect it, right? It's 3 spaces away from the y-axis, so I want it to be 3 spaces away from the y-axis, just in the other direction. So it'll be out over here. So there's my point that is symmetric with respect to the y-axis. All right, and what about the last option here? At least the last option that we care about, symmetric with respect to the origin. Okay, so that just means both, right? So this first point here was +3, +2, right? So symmetric with respect to the origin would be -3, -2. So left 3, down 2. So about right there. Okay, and it's called symmetric with respect to the origin because you'd have to look across the origin here to find the same reflected point. All right, so let's kind of generalize this a little bit. We had x comma y, right? It doesn't have to be 3, 2. It could be anything. This point doesn't even have to be in the first quadrant, right? It could be over here somewhere. You have a first x and y. So what's different about this point? The x is the same, right? It's the y that changed. It became opposite sign. It became a negative. So these two are related to each other by having an opposite y value. All right, similar to when you reflect something across the y-axis, you have the same y, right? Same height as the original, but the x is now changed, right? The x has changed its sign. And then across the origin, both the x and the y change. So that's actually a way you can test out if a point is symmetric with respect to the origin, right? You change your x and your y's to -x and -y and just kind of see if that makes sense. All right, well, okay, let me give an example to kind of maybe drive that point home. Okay, so our first example, example 1. Let's determine whether or not the graph of 6x plus 7y equals 0 is symmetric with respect, and we want to check all 3, to the x-axis, the y-axis, and the origin. Okay, and so what I just said a second ago is that if I want to test to see if it's symmetric with respect to the x-axis, I change my x and y. I change the y value. Okay, I change the y value. Okay, so let's do that. Let's do that. I'm going to look at my equation, 6x plus 7y equals 0, and I just said I'm changing my y to a negative y. All right, now I'm going to simplify this. 6x minus 7y equals 0. Okay, remember, if this graph is symmetric with respect to the x-axis, then this is a point of that graph, and this is a point of that graph. In other words, they should be the same graph. Okay, should give you the same graph, the same equation. So I'm going to compare the 6x minus 7y to the original 6x plus 7y. If I graph this one and if I graph this one, do I get the same graph? I do not, right? These are not the same thing. They're definitely not the same thing. And so we would have to say that no, this one is not symmetric with respect to the x-axis. Now we can test the y-axis. Remember, we're going to change, for this one, the x value. Okay, so again, these 2 points should be on the same graph. They should follow the same equation. Okay, so I'm going to start off with the 6x, going to change that in a second, plus 7y equals 0, change u to a negative x. Okay, so that's going to be negative 6x plus 7y equals 0. Okay, now I got to compare. Does this equation give the same graph as the original? And they do not, right? These cannot be made to look alike. So does this thing have symmetry with respect to the y-axis? No, it does not. Okay, next let's check the origin. Okay, remember for the origin, you have to change x and y to negative x and negative y. Okay, again, these 2 points should obey the same equation. They should give you, or they should be on the same graph. Okay, so let's change it out. So 6x plus 7y equals 0. I'm going to change u to a negative x and u to a negative y. When I simplify that, I get negative 6x minus 7y equals 0. Okay, here we go again. Is this equation, does that equation, whoops, give me the same graph as this equation? It's kind of a trick question because the answer is actually yes, even though they don't look alike. Because, okay, think about it for a second. If I divided everything by negative 1, right, that's something we are allowed to do to equations without changing the graphs that they give you, right? If you divide everything by negative 1, it changes how it looks, but it doesn't actually change the graph itself. So if I divided everything by negative 1, that would give me a positive 6x, a positive 7y, and, well, 0 is still going to be 0, right? So turns out, hey, look, it's the original. So we did it, right? Yes, this graph is symmetric with respect to the origin. Okay, so right, so you check all 3 of them. You look at each point, right? What has to change? Change y to negative y in the first one, x to negative x in the second one. You change both variables in the last one, and just check to see what happens. If you don't get the same graph on any of the examples, then you would say that there's no symmetry, right? Which actually most graphs will have no symmetry. Okay, anyway. Let's move on. I'm trying to think if there's anything else I need to say about that, but we can just jump to the next example. Okay, same idea. Same exact question, actually. Example 2. 5y equals 7x squared minus 2x. I want to know if this graph, if this equation, if I graphed it, has any symmetry. And we'll go through and check each one individually. I'll do the different colors there. I think that's kind of helpful. Okay, so checking the x-axis first. Remember, if you're checking the x-axis, you're going to change your y, right? You're going to change your y. I know the temptation's there to change x and not y, right? X-axis, you want to change x to a negative. But no, that's not what's going on here. Because remember, let me quickly sketch this again. If it's symmetric with respect to the x-axis, that means I have a point that's located down here, right? So what changed? Not the x value, it's the y value that changed from positive to negative. Okay, so anyway, just wanted to quickly remind you of that. Maybe it makes more sense now. Negative 5y equals 7x squared minus 2x. Okay, I want to compare that to the original. On the surface, it does not look like the original graph. Even if I went through and divided everything by negative 1, that'd give me a positive 5y, but then that changes 7x squared and negative 2x to positive, right? So even this is not the same, right? So nope, we don't have any symmetry there. So let me say that. Oops, I think I erased it too much. You know what? I'll just hit the backspace button. There we go. That looks nicer. Okay, so we would say no symmetry with respect to the x-axis. Okay, let's check the y-axis. Remember, for the y-axis, to check that one, you change your x's to negative x's. So 5y is equal to, when you square a negative, right, negative squared, the negative times a negative becomes a positive. So this is really just 7x squared. Negative canceled out. In this case, negative 2 times a negative x is a positive 2x. Okay, again, I check this one against the original. They're not the same, right? But if I do anything to try to change the sign of the plus, right? If I try to change that to a minus sign, I end up changing these as well. So, that one's going to have to say no symmetry with respect to the y-axis. Okay, what about the origin? Okay, well, remember, I have to change x and y this time. Negative y, negative x, negative x. 5 times negative y is negative 5y. We just talked about if you square negative x, it becomes a positive. So it's positive 7x squared. And negative 2 times negative x is a positive 2x. I just feel like I should probably go over this real quick. Sometimes people will want to write 49x squared here, right? As if this squared applies to both. And of course it does not, right? It only applies to what's inside the parentheses there. So that negative and the x are the only things that'll be squared. Okay, so no 49, just 7. All right, anyway, I see that mistake enough to make me want to point that out. Okay, so negative 5y equals 7x squared plus 2x. Well, how does that compare to the original? Right, the original here. It's not the same. If I try to go and make this a positive, right, then that makes this a negative and this turns into a negative as well, which is still not the same thing, right? So I can't actually make this equation look like that equation. So turns out this one has no symmetry at all. No symmetry with respect to the y-axis, the x-axis, or even the origin. All right, I want to do one more example like this. Let's see, do we have room here? Yeah, we do. Example 3. 3x equals the absolute value of y. Okay, remember what that means, right? Absolute value of a number is always going to be positive, right? So absolute value of negative 2 equals a positive 2. Absolute value of positive 2 equals a positive 2, right? It always gives you a positive. Just a quick reminder about that. All right, so let's check all three. X-axis, starting there. Okay, change the y to a negative y. And we just talked about this, right? Any absolute value of a negative becomes a positive, right? So this is actually the same thing as 3x equals the absolute value of positive y. Let me kind of break this up a little bit because maybe it's helpful, maybe it's not. This is understood to be a negative 1 times y. So what you should think about this as is negative 1 times absolute value of negative 1 times the absolute value of y. This equals a positive 1. And 1, so 1 here, 1 times the absolute value of y is the absolute value of y. Okay, so I don't know if that was necessary, right? Some people may have gotten something out of that, some people maybe not. But that kind of explains why there's still an absolute value around the y instead of it just being, y. Okay, clear all that out. Did too much there. Try that again. All right. So 3x equals the absolute value of y. Okay, I know you saw this in the very beginning, right? Those two are exactly the same. I don't have to change anything about it. So yes, this is symmetric with respect to the x-axis. Let's check that against the y-axis. It's possible to be symmetric with both. Okay, remember you change x to a negative x. That's going to give me a negative 3x here, equals the absolute value of y. It's not the same. Even if I divide both sides by negative 1 and make 3x positive, that negative still transfers to the other side, right? So they're not going to be the same. So I would say no, not symmetric with respect to the y-axis. And last one to check here, the origin. Change them both, x and y. Okay, the left side will become negative 3x. The right side, the absolute value of negative y is the same as the absolute value of positive y. We're back to this, right? Same exact situation as with the y-axis. So is this symmetric with respect to the origin? No. Okay, so that's how you can determine whether or not a graph has symmetry. Now, another related concept that we need to talk about is the idea of a function being even or odd, or neither. Remember, I said functions are the new numbers, right? And so functions can be even, odd, or neither, just like numbers, right? Numbers can be even, like, 2, 4, 0, negative 8. That's an ugly 8. Negative 8, there we go. They could be odd, like 1, negative 1, 5, 11, okay? They could be neither one, like, 2/3 or the square root of 5, right? They can be even, odd, or neither. Okay, functions do the same thing. Okay. So, what are we talking about? How can you spot an even function or an odd function? Well, first of all, we're going to use function notation. Okay, so, f of x. Okay, we're going to use that notation. Okay, so, a function f is even if you change the x to a negative x and you get the same function back. In other words, you plug in a negative x and it has no impact on the function. Okay? So what does that mean? Well, if I look at a graph here, so let's say this is x, and let's say you get a point right here. So you plug in a negative x, and you got a point right here, right? The same point. Changing the x to negative doesn't change the point. And it does that for the whole function. Well, that means, let's see, right, anything. Anyway, that just means that you have something, excuse me, something that is symmetric with respect to the y-axis. I'm losing my ability to draw altogether. There we go. Okay, so change x to negative x, see if you get the exact same function back. Okay, that's an even function. A function is odd if You change x to a negative x, and you get a negative version of the function. In other words, you get some negative y values. What does that look like? Okay, well, for every x value, you put in a negative x value, right? You go the opposite way. You get the negative version of that original point. So you're down here now. Let me do that a little bit better. Okay, so in other words, what you have here is some sort of odd function, or you have some sort of symmetry with respect to the origin. Okay, so put those ideas together. If you have an even function, it is symmetric with respect to the y-axis. If you have an odd function, it's symmetric with respect to the origin. We don't have anything for if it's symmetric with respect to the x-axis. Okay, don't have anything with that. Turns out, if you have something that has symmetry with respect to the x-axis, it's not a function. You might have to go back and look at definition of a function. It's not a function. Okay, so yeah, remember those and those two definitions. Okay, so let's do a couple of examples. I have 3 examples, so let's do those. Example 4. Determine whether or not the function f of x, which equals 1 over x squared, is even, odd, or neither. Okay. Remember the rule. No matter what you're checking for, change f to a negative x and see what happens. Does changing x to a negative x impact the problem? Okay, well, we already talked about this a few times. Whenever you square a negative x, you get a positive x squared. How does that compare to the original? They're identical, right? So changing f to a negative x ended up giving me the original. So the function is even. Right? So if everything gets back to normal, it's even. Okay, same question. F of x is equal to the cube root of x. Okay, so we're going to have to talk about cube roots in a second. Even, odd, or neither. I see a 3, so I'm starting to think that it's going to be odd, but, you know, we should probably think about that. Talk about it. Okay, anyway, no matter what, you still have to change x to a negative x. And think about what that means. Well, I'm going to break up that negative 1 and the x. Make it a little bit easier to see it. Well, I can rewrite that as the cube root of negative 1 times the cube root of x. Okay, and the cube root of negative 1. So what does that mean? Well, remember, cube root just means what times itself 3 times equals the number. So like 27. The cube root of 27 equals 3 because 3 times itself 3 times equals 27. So the cube root of 27 equals 3, right? Okay, what I just wrote is a bunch of mathematical nonsense, but I think you understand the idea, right? The cube root of 8 is 2 because 2 cubed equals 8. The cube root of 125 is 5 because 5 cubed equals 125. Okay, so that's the cube root. So now the question becomes, what is the cube root of negative 1? Well, negative 1, because negative 1 times itself 3 times. These two cancel out, become positive, but you're still left with a negative, and 1 times 1 times 1 is 1, so it's a negative 1. So the cube root of negative 1 is negative 1 times the cube root of x. So what's happening there? This is the original, right? That's f of x. So it's negative f of x. That's the definition of it being odd. How odd, right? Okay, so we talked about cube root, but let's kind of review exactly what happened here, right? You change x to a negative x, you get this. You simplify that to this. Oops, negative's too small. There we go. And you recognize this as negative the original. That is the definition of, here we go, an odd function. Negative the original. All right, let's do one more. The function this time is 7x to the third plus 4x minus 2, and I want to know if it's even, odd, or neither. Okay, as always, change x to negative all the way throughout the problem, all the x's, don't skip any. Okay, whenever you cube a negative, okay, remember what that means. Every pair of negatives, of course, become positive, but if you have an odd number of negatives, you still have a negative involved. So it's going to be a negative x, or 7x cubed. Almost forgot the 7 there. 4 times negative x is negative 4x minus 2. Okay, so now I compare it to the original. It looks kind of odd, right? Because positive 7x cubed is now negative 7x cubed. Positive 4x is now negative 4x. Negative 2 is now, stayed negative 2. This one was almost odd. Had this turned into a positive 2 for some reason, then it would be odd, right? Because everything would have changed. In other words, you could have written it as negative times the original, right? If that were the case, then it would be odd. But since that is not the case, right? Since this 2 did not change its sign, it stayed the same. Although it's almost odd, it is neither even nor odd. All right, so that's section 2.4.